Is Katharina Lorenz. I'm a researcher at INESC MN and at the Department of Nuclear Science and Engineering of IST. And I'm going to chair this seminar together with Dirkjan Verheij, who is also here. He has done his PhD on ion implantation in gallium nitride, so he is an expert in the material we will be discussing today, and he's a postdoc at INESC. So it's my big pleasure to introduce you to the speaker of today, Dirkjan Verheij. He's in his third year of the PhD in physics engineering at IST, and he will show you his results on fabrication and testing of radiation sensors based on gallium nitride microwires. So Dirkjan, if you are ready, please go ahead.
I am ready, and I will share my screen. Okay.
If you can just put it in presentation mode.
Okay, can you see it?
Perfect, thank you.
Perfect. So hello everyone, and thank you for the kind introduction, Katharina. So I was invited to give this month INESC MN internal seminary, and the topic I chose to talk about is gallium nitride microwire radiation sensor for medical dosimetry. And I've been working on this topic since my master thesis, so since 2017-2018. And in this talk, I will be talking a little bit about the results we had along these years and the potential application we envision for this research. However, I will start with a brief introduction, especially because I am aware that at INESC MN not everyone is a I hope to also give you introduction about this topic. So starting with the kind of radiation we are interested in, which is the ionizing radiation, and is called this way because the radiation has sufficient energy to ionize atoms and molecules in materials. So contrary to, for example, visible radiation, which only excites atoms, the ionizing radiation ionizes the atoms and molecules. And there are several different kinds of ionizing radiations. We can divide the radiation basically in particle radiation, and within the particle radiation we have alpha radiation, beta radiation, and eta radiation. And then we also have the electromagnetic waves, which are the X-rays and the gamma radiation. So, and since the discovery, or the first discovery of ionizing radiation, which was by Mr. Röntgen in or at the end of the 19th century, when he observed for the first time the X-rays, the development and research on devices that were capable to detect ionizing radiation began, and nowadays radiation sensors play a vital role in many fields and applications, such as in medical application, in research, in the control of environment, in space technology, and in nuclear energy. So, and as is the case for most semiconductor technology, the current technology is mainly based on silicon, which obviously has the advantage that silicon technology is very mature. However, silicon is not known to have a very good radiation resistance. And this creates a question if the current technology based on silicon is actually good enough. So in this question led to a lot of research on other materials. And one of these materials is gallium nitride, which is a member of the group 3 nitride semiconductor family, and probably best known for its application as the blue LED, which was the topic of the 2014 Nobel Prize research. And gallium nitride has a lot of very interesting properties. So it has a wide bandgap of 3.4 electron volt, which makes it essentially visible or blind to visible light. It typically grows in a root-side structure, which is a hexagonal crystal lattice, as we can see here. It has a high thermal conductivity, a large breakdown fields, but especially important for radiation applications. It has the atoms in the crystal lattice have large displacement energies, and the material presents a strong defect mobility at room temperature. And I'm going to show you here why these characteristics are important. So if we take a look at this graph on the left, which shows the displacement energy thresholds in function of the reciprocal lattice constants of several materials. And for those who do not know, the displacement energy is basically the energy necessary to remove an atom from its original position in the crystal lattice. And basically, the higher this energy, the more difficult it is to replace the respective atom. And consequently, the higher the resistance of the material to radiation. And as we can see here, gallium nitride is located all the way up here. If we compare it with, for example, other typical semiconductors used for radiation detectors such as germanium, silicon, or even gallium arsenide, the value of our gallium nitride is much higher. And then at the right side, we have another graph which shows the relative defect level in function of the irradiation fluence for A, C, and N-plane gallium nitride. And this graph actually has a lot of information, and I'm not going to cover all this information because that would be outside of the scope of this talk. But I want you to focus on the evolution of the relative defect level for fluences until 10 to the 15 or 10 to the power 15. And as we can see here, the relative defect level starts to increase linearly for the lower fluences. But then at this point in region 2, the relative defect level actually stabilizes. And this stabilization occurs because the density of defects is high enough for the defects to recombine with each other. Like I said, gallium nitride has a high defect mobility at room temperature, and this defect mobility basically causes recombination of the created defects, and this then stabilizes the creation of defects. And this effect is called dynamic annealing, and materials who have a strong dynamic annealing effect typically also present a higher radiation resistance. However, there are also some problems with gallium nitride, and one of these problems is that it is relatively difficult to grow gallium nitride epitaxially, or it's difficult to grow high quality gallium nitride. And this is because of the lattice mismatch between gallium nitride and a typical growth substrate, which I show here in this schematic. So here we have a sapphire substrate, and the mismatch between the gallium nitride and the sapphire, which basically means that the material does not fit well on the substrate, creates a strain in the crystal lattice, and this strain leads to a very high density of dislocation defects. So here in this transmission electron microscopy image, we can see all these black lines, and these black lines are all dislocation defects. And these dislocations then limit the carrier mobility and also increase leakage currents, which is obviously not a desired property when creating devices. So this could be overcome by growing very thick films of gallium nitride, but this has the downside of having very high costs. So we opted to not use thin films or bulk gallium nitride, but to invest in microwires grown by metal organic vapor phase epitaxy. And in a very simplistic way, these wires are grown like this. So first, small islands are grown on a sapphire substrate, as you can see here. And then the growth conditions are such that especially the vertical growth is stimulated. So instead of growing laterally, the wires grow only in the vertical direction. And in the end, we obtain an entire forest of microwires in the vertical direction. And if we then look at the TEM image of a single microwire, which is shown here, contrary to what we observed in the previous slide, we do not see any black lines along the vertical axis of the microwire. And this means that the microwire is essentially dislocation free. So this does not mean that the mismatch between the sapphire and the gallium nitride entirely disappears. It still exists. Because if we zoom in at the bottom part here, where the sapphire GaN interface is located, we can see that the mismatch still exists, as shown by the black arrows here, but that the dislocations are bended towards the side wall of the microwire because of the specific 3D nature of the structure. So they are relaxed and bended towards the side wall of the wire, very close to the surface or to the substrate. And the rest of the wire, like I said, is kept essentially dislocation free. So if you're now wondering, where at INESC MN we have these machines that grows these fantastic wires, well, we do not have this machine. The wires are actually grown in France, in Grenoble, and they were kind enough to provide us with two types of microwires. So we have here the schematics of the microwires, and we have on the right side wires which are entirely n-type doped. So we have the bottom part which is heavily n-type doped, and then the top part which is moderately n-type doped, and these doping concentration are a consequence of the growth process. And then here we have essentially the same sort of wire, but around the top part of the wire, a thin p gallium nitride shell is grown, which creates a p-n junction in the radial direction from this point to the top of the wire. So then with these wires, we create our radiation sensors. And in this slide, I show the several fabrication steps we follow at INESC MN. So we start with a titanium tungsten deposition, which after a lithography step and an etching step creates these small crosses on the substrate, which are alignment markers. And I will later on explain better why we need these alignment markers. And then we do a SiO2 deposition to isolate the substrate from the microwires, which are then deposited on the silicon oxide. And then we do two more photolithography steps, followed by metal depositions to create the contacts at the extremity of the wires. And we do two because we want different contacts at the P and at the N gallium nitride extremities in order to obtain ohmic contacts. And so here I show you what the devices look in real life. So we have on the left side the N-type conductive device using the N-type gallium nitride wires. And in this case, we have samples with both chromium gold contacts or with titanium aluminum titanium contacts. And these contacts usually give us ohmic contacts, while these create nonlinear contacts. And here at the right side, we have a p-n junction diode device. And if we look here at the p gallium nitride extremity, we can actually see that the diameter of the wire is slightly larger, which is exactly because of the additional p gallium nitride shell. So like I said, I wanted to highlight a specific part of the microfabrication process involving the alignment process. So, and this has to do with the wire dispersion and how we perform this step. So to put the wires on the device substrates, we put a small piece of the original growth substrate in IPA and apply some ultrasounds to it to detach the wires from the growth substrate. And this creates this suspension of microwires inside the IPA. And then we basically just put some droplets on the device substrate. We wait until the IPA evaporates. And this results in a nicely uniform and without clusters dispersion of the microwires. However, the problem here is that we do not have any control of the position of the wires. So the wires are displaced randomly on the device substrates. And this is difficult because this means that every time we are fabricating a new sample, we need to redo the drawing of the contact lines. And as doing this individually for each wire is quite a time-consuming step, I developed a software which does this all automatically using images I take of the device substrate. And I will show you here how this works. So this is a starting image where we have here the 4 alignment crosses I talked about earlier, which act as references for the position on the device substrate, with several microwires dispersed. And then the software basically detects the structures present in the image. So we have the 4 alignment markers and 1 of the microwires present in the image. And it gets the relevant coordinates. So, and as we can see here, it even can distinguish between the P part of the wire and the N part of the wire. So because of the increased thickness of the P part. Now, and with these coordinates, it then calculates the coordinates of the contact paths, which are led to predefined position in the lithography mask. And the data is then transferred to a AutoCAD file, all automatically. And then after the lithography, metal deposition, and metal liftoff, this is the final result. So, and this is all done automatically. The only thing I have to do is take the pictures, and this saves me a lot of time. And if maybe anyone is interested in using this kind of software or my knowledge about it, feel free to send me an email or come talk to me, because it can be helpful. So just to show you then what we are working with in the end. So here I show a microscopic image of the final device. So each of these substrates can hold up to 36 devices, and the sample is cut and put on a chip carrier, and wire bonding is done so that we can take the chip to the lab where we do all our characterization, which is mainly done at CTN and not at INESC MN. So we always start first with some electrical characterization of the devices. And the way I'm going to present the data is at this part of the presentation, I'm going to show you the results of the N-type conductive devices on the left and the results of the PN junction diode devices on the right. And so starting with the conductive device, we see that the non-annealed curve IV curve is asymmetric and nonlinear, which means that there are some kind of potential barrier at the metal semiconductor interfaces. But after annealing at 600 degrees Celsius for 60 seconds, we obtain a nicely linear IV curve, meaning that the contacts have become ohmic. So the electrical property of the PN junction diode is obviously completely different due to the rectifying nature of the device. However, we still see an improved electrical characteristic after annealing. So the forward bias current shows an increase, and also the threshold voltage at which the current starts to increase lowers. And this again means that we are lowering or even eliminating potential barrier at the metal semiconductor interface. Then I also want to highlight the very low dark current we obtain. So in this case, lower than 1 picoampere, which is the resolution limit of our measurement equipment. So then before irradiating our samples with protons, we always like to do some photoconductivity studies, because these are protons damage the device and UV doesn't. So it's always a good way for us to see the properties of the device and how they behave when illuminated by UV light. So in this case, we use a UV LED with a typical wavelength of 365 nanometers. And we can see that the results of the conductive device and the PN junction diode are completely different. So in the case of the N-type wires, we only measure a very small photocurrent signal, while for the PN junction diode, we actually measure a photocurrent to dark current ratio over 1,000 at zero bias. Then when moving on to transient measurements, and at these measurements, we fix the applied bias and turn on the light at some point to turn it off again at some point later in time, and then study the transient photocurrent, we can see that the differences are even more. So in the case of the n-type conductive device, we measure a very long decay time. So in this case, when it takes the device over 2,500 seconds to go from 90% to 10%, while in the case for the PN junction diode, the rise in decay times are actually below 22 milliseconds, which is again the measurement limit of our equipment. So this gives the idea that the PN junction diode devices are in every way much better than the conductive device. However, there's one point at which the n-type wires are better, which is that when measuring the photocurrent, the absolute photocurrent in this case is around 50 microampere, while for the PN junction devices, the absolute photocurrent is only of 1 nanoampere. And this actually also translates in a higher sensitivity of the n-type wires, or better said, a higher responsivity to light. So this means that we need a lower intensity of light to obtain a readable signal with the n-type wires in comparison to the PN junction diodes. And this has actually a consequence that, for example, with the n-type microwires, we can do photocurrent spectroscopy measurements, at which the light is divided in individual wavelengths using a monochromator, which we cannot do yet for PN junction due to this low responsivity. So because of the division of the light in individual wavelengths, the intensity is much lower. And when illuminating the PN junction, we actually cannot read a electrical signal, and consequently, we are not able to perform this measurement. Now, talking a little bit about the measurement itself, as you can see here, when approaching the wavelength corresponding to the band gap of gallium nitride, we see that the photocurrent starts to increase, and this really shows that it is gallium nitride we are measuring and not something else. So now moving on to the actual important part of our work, which is the irradiation of the samples, which we do at Campus Tecnológico Nuclear at the Ion Beam Accelerator facility, of which I show a map here. And we use for our experiments the Van de Graaff accelerator, which can accelerate protons up to an energy of 2 mega electron volts. And these protons are then directed through this line here to the microprobe chamber. And this microprobe chamber has the interesting feature that it can focus and position the beam to a micrometric scale. So the beam spot size we use during these irradiations is actually of a size of 2 by 3 micrometer. And we also can position the beam with this same precision. So in the chamber, furthermore, allows for a series of detectors to be included. So we have an X-ray detector, optical lenses, the electrical wires can be connected. So this allows for simultaneous electrical measurements, proton-induced X-ray measurements during the irradiation. So from this, we can extract actually a lot of information. So I will now deviate a little bit from the way I presented my data so far. So right now, I'm only going to talk about the n-type microwires to begin with. And I want you to look at this graph here on the left side, so which shows the strong decay of conductivity with increasing irradiation fluence. And so despite the high radiation resistance of the devices, the damage that is created by the proton beam is still high enough to induce a strong decrease of the conductivity of the devices. So as you can see here, the red curve represents the non-irradiated sample, and the green, blue, and yellow curve, the electrical IV curves after irradiation with these fluences. However, we still, after applying a very short beam of irradiation, and short exactly because we wanted to avoid creating too many defects during these measurements. We saw that the evolution of the decay of the ionocurrent is very similar to the one shown before using the photocurrent. Then, so like I said, we are able to really position the beam, the proton beam, with a micrometric precision. And this allows for us to irradiate specific sections of the device. And we did this because we wanted to study the influence of the contacts in the ionocurrent signal. So we irradiated each of these sections individually and measured the ionocurrent, and we actually saw that for both negative and positive bias, the highest peak was obtained when irradiating the middle section of the sample. And in fact, it looked like the contacts were actually in some way suppressing the ionocurrent signal. So that's how far our measurements of the N-type microwires go. Moving on to the p-n junction gallium nitride microwires, I start by showing a proton-induced X-ray map of a specific area, and this map basically represents the emitted X-rays from the materials present in the irradiated area. So in this case, each material emits a specific X-ray with an energy which can be correlated to the material. And so we can see here the gold coming from the gold contact, then the green gallium nitride signal coming from the microwire, and the blue dots coming from the tungsten in the titanium tungsten aluminum contacts. And just as we did for the N-type microwires, we decided again to irradiate specific areas of the device. And in this case, actually, we have very different areas. So at one side, we have the p-n junction, and at the other side, we are only irradiating the N gallium nitride because, like I said before, the p-n junction is only located at the top part of the wire. And we see that the results are completely different. So when irradiating the p-n junction, we actually obtain a signal similar to that one measured with the UV light. And when irradiating the N gallium nitride extremity, the ionocurrent response is almost negligible compared to the dark current. And so this means that it is really the depletion region created by the p-n junction, which is responsible for the creation of the ionocurrent signal, and that the N gallium nitride part has a low influence on the signal. So then moving on to the transient measurements that we did while irradiating the p-n junction again, we actually saw, and this is maybe the most surprising result, that there wasn't any decay of the ionocurrent during the irradiation. So when irradiating it for 25 seconds, the ionocurrent table actually maintains a stable value, and we see no decay at all, which was obviously not the case when we were talking about the N-type microwires. We do observe a slightly lower signal ratio when comparing the data to the photocurrent data, but this doesn't have to mean much, because one thing I haven't said here, which is important to understand, is that when we irradiate a sample with UV lights, the photons are all absorbed at the surface, or at least close to the surface. They do not penetrate inside the semiconductor. With protons, the story is different, because actually the protons with an energy of 2 megaelectron-volt have a range of 53 micrometers in gallium nitride. So what actually happens is that the protons cross the wire and only deposit part of their energy in the active area. So this could explain why we observe a lower signal ratio compared to the photocurrent measurements. So then finally, I want to also show you the evolution of the dark current with increasing fluence, or with irradiation, proton irradiation with increasing fluence. So here I show in the blue the original IV curve, and we see that for a fluence of around 6 × 10⁻14 protons per square centimeter. We do not see any increase in the leakage current, but only a degradation of the forward bias current. And this degradation is maintained or is continued when increasing the fluence. But at higher fluence, we finally also see some increase of the leakage current. So, however, this increase in the leakage current is actually relatively low when compared with devices in other literature. So then finally, we also have started some recent collaboration with people from the University of Aveiro and investigators from the University of Valencia. And this collaboration basically have the aim of doing micro-Raman and microphotoluminescence spectroscopy on our devices, and also Kelvin probe measurements on the PN junction devices. So then arrived at the final part of my talk, where I'm going to talk a little bit about the application or possible application of our samples. And we identified that they can be mainly interesting for dosimetry and medical applications. So as you perhaps know, for treating several types of cancer, ionizing beam therapies are common and popular. So we have the proton beam therapy, X-ray therapy, and also brachytherapy, where radioactive seeds are placed directly inside the body of the patient. And in these kinds of therapies, it's very important and fundamental to have a very good control of the dose that is put into the patient, and also of the position, of the angular dependence. So being able to measure the dose in real time and in vivo is very important. And right now, that is not, there is a lack of good detectors for this. So in this sense, we hope that our samples might revolutionize in some way this technology. And in fact, we have some research of which we can base, or on which we can base ourselves. As in the last years, research has been done on gallium nitride thin films for X-ray dosimetry, as you can see here, and also gallium nitride Schottky diodes have been applied as proton beam monitors. And our objective is really to try to show that our microwires are at least as good as these technologies, or maybe can even exceed the results shown here. But to achieve this objective, we have still obviously a lot of work to do, a lot of rocket science left. So, and this all begins with more characterization. So there are still a lot of questions we have left regarding the properties of our devices. And we are talking, for example, about charge collection efficiency, responsivity, and sensitivity to other types of ionizing radiation, such as X-rays or gamma rays. And then, as you all know, at INESC MN, we are always trying to improve the fabrication process of our procedures. And in this specific case, we also want to find a good way to scale our devices from having only one microwire to having several microwires. And we are actually aiming to use flexible substrate for this. So in this case, I show an example where researchers have used PDMS to achieve this objective. And then obviously we have the electronics. We need to identify which electronics are necessary to optimize the readout signal. And in the end, there will be a lot of more characterization to do. So when we are talking about applying these sensors in vivo, so this means inside human body, we need to know how the tissues of a human influence the readout signal of the radiation sensor, and therefore we need to do experiments in human phantoms, and obviously a bunch of other stuff such as angular dependence study, energy dependence study, and much more. So, and here I finish my talk. I want to thank everyone who is part of our research group at CTN, and who always not only provide with useful help, but also with a good working environment. And obviously all the people at INESC MN, which actually do precisely the same as the people at CTN. and it's really a nice, or both are nice places to work, and I do it with a lot of joy and love. And finally, I want to thank all the audience for listening to me. And if you have any questions, I will be very pleased to answer them.
So thank you very much, Dirkjan, for this very nice talk, in which you talk it a lot on radiation sensors and for the microfabrication and ion beam engineering. So it was very, very, very nice. And so if someone have questions, or you can just click on the level or you can directly desactivate your mute and start to ask the question.
Okay, so if no one steps in, I will ask a question. So in your slide 6, you show the islands. So they are. I'm not sure I understood exactly how that is done. So you show separated islands.
Yes.
And then you grow the microwires by MOF. But how do you have those starting islands, and can you control the growth so they don't expand through all the surface and they remain islands, or that is a bit difficult to control?
Yes, so the way this works, so first of all, so I have never done this process myself. Like I said, this is done in Grenoble, in France. But the way this works is that first they start with depositing a silicon nitride sort of mask on the sapphire substrate. And the silicon nitride mask basically is not complete, so there are voids in the mask. And then they do nucleation of these kinds of islands or seeds, which are of gallium nitride. So these seeds are formed at the voids of the silicon nitride. Then to promote the vertical growth instead of the lateral growth, they actually figured out that by applying or introducing a Silane flux during the initial stage of the growth, they could suppress the lateral growth and only really promote the vertical growth. So this Silane flux is responsible for then the vertical growth, and when the wires reach like around 10 micrometers, this Silane flux can be turned off and the vertical growth will continue in the C direction. This is actually also the reason for the different doping concentrations here. So the heavy doping of the bottom part is a direct consequence of the application of the Silane flux.
Thanks.
So there is more questions. So if
so I have my hand raised. Can I go?
Yeah, Virginia.
So thanks for the very nice talk, Dirkjan. It was very interesting. I have a question. You showed this degradation during the proton irradiation of your PN junctions. Is that reversible?
So let me just go to the slides. This slide?
Well, no, later when you show the degradation of the forward current. Yes.
Okay, so in principle, yes, it is. So we can do annealing to recover some of the defects created during the irradiation. However, we have not done a lot of studies in this sense yet. So this is still some work that is ongoing. But we have observed that for the N gallium nitride samples, we were able to not completely recover the electrical properties, but we were able to recover at until a certain amount. So we are not sure if in this case, for example, the leakage current is going to be reduced after annealing, but we do surely expect that part of the forward bias current can be recovered.
What about if you fix a fluence and you expose it over long times? Do you also observe a degradation with that?
Sorry, I'm not sure if I understood.
If you have the wires, so you fix the fluence, but you look at the IV curves versus different times of exposure. Do you also observe degradation with time of exposure?
So actually, the fluence is a parameter which depends on the time of irradiation. So.
Oh, I see. Okay. So it's not just the intensity.
Exactly. We have a certain proton flux.
Yeah.
And the fluence is calculated by multiplying the flux with the irradiation time.
So in these two cases, you have the flux is.
The flux is constant.
It's constant. Okay. Okay. So I didn't understand that. Okay.
What differs? Yeah.
Oh, and well, if no one else has a question, I have one other thing. You mentioned that you couldn't get enough intensity out of your monochromator in order to do the spectroscopic measurement.
Yes.
Have you tried to just use bandpass filters with your light source? That will probably allow you to get a much higher light intensity, and you can still get some spectroscopic information, of course, not so fine like with a monochromator, but you might be able to get some information if you have a set of bandpass filters.
Okay, we actually haven't tried that. We don't have such bandpass filters available here at CTN, but that's a very good suggestion.
Yeah, you'll get much more intensity than in a monochromator.
We will definitely, or I will definitely look into that, because
Okay.
that sounds quite interesting.
Okay, thank you.
If I can, Dirkjan, Veronica. So it's more a futuristic question. If this is to be inserted in the human body, ultimately, it's the ultimate goal, right?
Yes, one of the goals, yes.
And it needs to be biased. How are you planning, or what is the vision for the powering of the device?
Okay, so this is actually one of the very interesting properties of the PN junction wires. That is that they are in a way self-powered. So as you can see in this slide, the response at zero bias is very similar to the response at an applied negative bias or reverse bias. So in this sense, they actually don't need to be necessarily powered with a bias to obtain a readout signal. So that would probably, if the objective is to insert the sensors inside the human body, this would be quite beneficial.
Okay, thank you. Great.
Is there someone have more questions?
Hi, I was wondering, what is a human phantom experience?
Okay, so basically that is an experiment where, okay, well, I don't need to go to the slide. It's an experiment where we use a human-like tissue in front, for example, of the radiation sensor, which obviously influences the irradiation. But which is not really a human. So, and this can be, for example, a volume of water, but it can also be bone tissue or some kind of organic material that simulates the human skin, really anything like that.
No, okay, thank you.
So,
may I ask a question? May I? You have to check the raised hands. Dirkjan, this was very nice. One thing I had thought about, so this issue of placing nanowires and microwires on a substrate is always a vexing issue, right? one thing that some people have tried is to use, for example, microfluidic system. So if you have some channels, you don't need to seal it against the substrate, right? But you can just gently lower it on the substrate. You have a solution with your nanowires, and then you use the microchannels to channel them. And because you have a very controlled flux, you probably can position them exactly where you want them. Then you can lift this PDMS microfluidic array, and your things will be all in the right place. I'm not saying that this is easy, but it's something that we have the know-how to attempt.
Okay. That sounds really interesting. It sounds a bit scary to me, being said like this. But so I think that right now, for my needs to create single wire radiation sensors, this works well enough. So I can easily create up to 100 or 200 single wire devices relatively fast. I think that the problem here is a little bit about exactly creating devices containing more than one wire. So one of the strategies is to create a matrix where the wires are in the vertical position, but this might be a very interesting strategy to create multi-wire samples at which the wires are actually in a horizontal position on the substrate, because this way of creating devices like I'm using now is not, I think, very good for that, because of the error that's always existent when using the image analysis software. So like I showed, for example, we can less or more distinguish between the P side and the N side. However, sometimes the software fails to do this, which is normal. And if we have a multi-wire device and one of the wires is switched around, this could compromise the entire electrical behavior of the sensor. So I think that I don't know if during my PhD this is something we will attempt to follow due to I have less or more 2 years left, but maybe we can discuss this at some point and think about it, because it sounds very interesting.
Okay, thanks.
Yeah, just to continue on what you were saying. So you use a software that you probably programmed yourself, right? Yeah. And you were saying that it has some limitations on defining exactly what the position of the wire. So do you have an idea of the difference the both ends need to have in order to always get the correct configuration of your system? And if that can be used with different shapes, for example?
Well, the first part of the question. So if we look at here at this microscopic image, for example, and we look at the wire that will eventually be selected by the software, which is this one, we are having, so this image is taken with a microscope with an amplification of 50, if I believe correctly. And we ourselves, when looking in a microscope, have quite a hard time distinguishing between the N side and the P side. So if we look here, we can say that, okay, this side looks slightly thicker, so we will assume that it's the P side. In the sense of the limitation of our software, I do not expect my software to be better than my own eyes. So if we are having difficulties to distinguish the P side from the N side in the photo, I think that the software will have slightly more difficulty. We could obviously improve this by having better photos. So for example, if we would use SEM microscopy instead of optical microscopy, it would be easy to distinguish the P side from the N side. However, that would lead...
But wait, when you have SEM, you need, so your surface is conductive?
No, but I am able to see the wires in the SEM microscope without any contacts deposited. So in the SEM images I showed, we have the contacts, which makes it easy to find the wires, but even without contacts, I'm able to locate the wires and take pictures. However, this would increase the time it takes to to perform this process with like a huge amount. So we need to find, or I need to find some way of the time benefits and result benefit. But if the structures would be slightly larger, talking for example about 100 or 10, even tens of micrometer, I think that this would be absolutely super reproducible, because so these crosses are actually 12.5 micrometer by 12.5 micrometer, and they are perfectly defined in the image analysis software. So I don't think that would be a problem.
So more questions. If nobody have question, I have 1 or 2 questions for you, Dirkjan. So in your slide 9, can you show it again in your IBIX profile? I think in 19th, yeah, it's 19th.
19, okay.
Slide 19th, I think, yeah. 1, 2. Yeah. Here, as I understood, you so you said that, I think, as I understood you said that the increase of the conductivity is due to the radiation, right?
Yes.
And the contact doesn't make any contribution?
Well, we were actually expecting a contribution from the contacts, because in this case, we had nonlinear devices. We were analyzing nonlinear devices, so we expected some kind of potential depletion region to be present at the metal semiconductor interface. So we actually did the study mainly to see if the ionic current signal would be improved by this potential barrier at the contact region. However, actually what we observed was the contrary. So in this case, actually we see some kind of a suppression at the contact regions. And we are not entirely sure why this happens. One thing we have to note here is that our beam is not the most stable beam in the world, so variations in the punctual flux might exist, but the fact that we actually observe a very good correspondence between the results at negative and at positive bias really indicates that the contacts potential barriers are not influencing at that much here. So the reason why we observe lower signals might be because of the metals deposited on top of the wire, but the protons should cross these metals with ease. So we're not sure why we observe this effect, but we can from these results conclude that the contacts, or that the signal really comes from the bulk region of the wire. I don't know if Jibril is still present.
I think he left, or he got kicked out. Oh no, there he is.
Don't know if he heard my answer right now.
Yeah.
Okay.
I am back, so I have problem with my connection. Okay. So the other question I have is on the slide 21, which show your UV dark. It's a little bit. Maybe I will deactivate my camera. Those are the same devices, because it's really different. It's very different. Those are the same devices or not?
It is the same device.
As I can see, the IV dark is
Okay, if I understood the question correctly, you're asking why the dark current in both graphs is so different from each other. And this has to do with the fact
so different, yeah.
Yeah, so this is because actually the curve on the right side was measured after we did the irradiation on the PN junction.
Okay.
And also after all these transient measurements. So at this point, we had irradiated device already with a fluence of one or a relatively high fluence, close to 1 × 10⁻⁻16 per square centimeter. So here we are already observing the increase of the leakage current in reverse bias and the decrease of the forward bias current. So that's why we actually observe a difference in the dark currents, but it is the same device. And actually, to really confirm these measurements, and we have done, or we saw similar effects on other samples, but to really confirm these results, we should actually redo the measurements and start by irradiating the N gallium nitride part and irradiating the PN junction afterwards. So changing the order and see if the results are the same, but I do expect that we will not see a different behavior here. But that's the reason why they look different but are the same.
So thank you. There is more question? If there is no, I have one more, maybe. So do you think that it is possible to have devices based on N-type nanowires, microwires? So
if it's possible to have devices based on PN junction microwires?
Yeah, if there is a possible, yeah.
Definitely. I mean, I think that
on N-type, so only on type nanowires.
On N-type. Yes, I think that the results I showed where so I think that this is the main result where we can identify that the N-type microwires might have an application, because so due to the nature of the N-type microwires, and actually the very long decay times are also a result of this, these wires might present a mechanism which creates internal gain. So this means that actually the electrons that contribute to the photocurrent signal are more than the electrons that are created by the ionization or excitation of the light or proton irradiation. So this internal gain could potentially lead to very high signals for low intensity beams. And if we have an application where decay times or long decay times are not an issue, I think that this can definitely have an application. Regarding the damage created, I must say that the fluences we are applying on the wires are relatively big. So maybe if we apply a lower fluence, which is difficult to do with our experimental setup, but for example, of 1 × 10⁻12 protons per square centimeter, maybe the damage created would even be lower. And in this case, we might have also used these samples for dosimeters. Depends a little bit on the necessary specifications of the application.
So thank you. Maybe one more. So you show that the PN devices are stable during the measurement, right?
Yes.
So application you are targeting, or
sorry?
Or do you hear me?
Yes, yes.
Yeah. So it is enough for application you are targeting or not?
Well, that's hard to say with only this measurement, but we need to believe it, because if we wouldn't believe that our results are good enough to eventually apply these devices to a specific application, maybe we would have to question ourselves if it would be worth to continue this research. But at this point, we firmly believe that we have a good enough basis to achieve this. So in that sense, the answer to your question is yes.
Okay, so that's good, very nice. So thank you very much. And if there is no more question, I think we can close the session. Any more question?
No,
No.
I believe we can close the session. So I want to thank everyone that joined our session today. And I would like to announce that next week, March 5th, we will have our March seminar with Professor Tiago Costa. He was a PhD student at INESC ID, and now he is assistant professor in the Department of Microelectronics in the TU Delft. So I salute, of course, his talk, but I want to ask you to join this, because this will be a very, I think, very, very nice talk. And have a good weekend.
Thank you. Bye-bye. Have a good weekend.
Bye-bye. Have a nice weekend. Thank you, Dirkjan.
Bye-bye.
Thank you so much, Dirkjan. It was a really, really good talk.